Hello there, this is Adam Scriptjack from STC, and I've got a question for you. Do your models look like this? Lots of layers of decomposition, blocks composed of blocks all the way down. This means you may have done a lot of system engineering without breaking your modeling effort into manageable chunks. For some folks this may be fine, but imagine if you had a system with 10 parts or 20 parts. As systems can become very complex, imagine if each of those parts had parts and so on and so forth. How would you be able to manage multiple modelers working in the model without stepping on one another's toes? How would you employ configuration management? How would you manage the interfaces between these components? How about your requirements and relating them back to each system element that they specify? Well, the solution is simple. Take a structured black box, white box approach. So what are black boxes? A black box is a view of a system taken from a purely external perspective. The systems or components, inputs, outputs, and general functions are known, but the internal contents or implementation are unknown and may even be considered irrelevant. This is a problem-solving technique with roots going back to the early days of computer science, where hardware elements, such as computer chips, would have different output combinations based on sets of differing input combinations. This concept is also useful in systems engineering, where we want to support the implementation of a system and its components in terms of make, buy, or reuse, without needing to specify the internal details. A system can and should be defined from a black box perspective initially prior to decomposition as a means of truly understanding the system boundary, its attributes, observable states and functions. And when it's complete, you may then white box the system into black box components. Then once you define those internal components and have made implementation decisions for them, you may choose to white box those if you need to define them further. This is considered a top-down progressive refinement of the system, and it enables you to segment your model and organize it in such a way to support multiple modeling teams and enable configuration management. Here we have a BDD, which represents a notional missile system on a block definition diagram as part of a domain. It has attributes which describe performance, physical constraints, references to an interfacing system, a proxy port, for that interface, and even operation representing its behavior. Because it has no parts, this could be considered the black box specification for this missile system. Now let's say we want to take the black box and decompose it into a white box. Well, SysML provides us with a generalization relationship which supports inheritance and redefinition. We could take the black box block and generalize from it to a new block which represents the white box view of the system. This could support alternative architectures such as logical architectures or even physical architectures. Through generalization, the white box inherits structural and behavioral features from the black box and may redefine them as needed. Here we see the missile system with two specializations, one logical and one physical. As you can see, the caret symbols on the left indicate that these are inherited properties from the original missile system and may be redefined as needed. These specializations are also composed of parts, respectively, because they themselves are white boxes of the system itself. These white boxes can be composed of parts with their own structural and behavioral features that then may interact to support a system-level behavior and be treated as black boxes themselves. For example, here we have a logical architecture for the missile system with its components. In this example, the movement controller required further decomposition. So here again, we leverage the generalization relationship to create a specialization that can then support that further decomposition. The same is true with the physical architecture. Here we have software and hardware components of the missile system, and these may also interact to support a system-level behavior. These will also have their own behavioral and structural features defined. And here again, with this example, we see that the payload hardware component required further decomposition. So we created the specialization below that inherits from the payload, and we see it's now comprised of a fuse and an explosive. Lastly, here's a package model view of this approach. Since the black box is a general classifier, it can be kept in one model, and the white box can be further developed in another model where it specializes from a usage containing the black box. In this example, the logical model uses the black box model and inherits accordingly to support the development of a logical architecture. Then the physical model can use the logical model and inherit from the black box via that model and its nested usage to support the development of the physical architecture. This approach can support a CM strategy by controlling access to each usage upon a baseline and enable the model to support a growing modeling team without interfering with one another. So imagine this kind of going down further and further as you decompose each component. You can create new models for those components and assign modeling teams to further develop those. The black box, white box approach is very useful as it forces you to approach your system development through a progressive refinement, where each lower level of decomposition is done in a disciplined and structured manner, and concerns are addressed accordingly at each level. Hopefully this video helps you employ a black box, white box approach on your project. Have you used this approach in your MBSE practice? Well, let us know down in the comments.